Hello, my name is Munadir Ahmed and I'm an applications engineer at PLECS. I'd like to welcome you to this tutorial video on thermal modeling in PLECS. PLECS allows for the modeling of thermal losses and the associated thermal aspect of power electronic systems so that engineers can estimate efficiency, component temperatures, and view temperature cycle waveforms. In PLECS, ideal switches are used to represent power semiconductors. They are either in the on or off state. Toggling a switch is an instantaneous event that requires only two simulation steps, one right before and another right after the switching event. This makes the simulation of complex circuits very fast, especially if there are many power semiconductors present in the circuit. However, when using instantaneous switches, there's no information about the transient waveforms during turn on and turn off. Thus, switching losses cannot be calculated by multiplying the voltage and current. In this video, we will discuss how the switching and conduction losses are modeled in PLECS in conjunction with the ideal switch concept. Additionally, you can use the thermal domain to model the thermal structure of a device and its cooling system and estimate the associated temperatures. PLECS uses a lookup table approach to calculate losses. The PLECS semiconductor devices all have a thermal description parameter that can be specified by the user. The data used in the lookup tables can be found in the datasheets or obtained through measurements in lab. We will start with a simple representation of a buck converter. In this circuit, the inductor is modeled as an ideal current source. An IGBT is used to gate current from the ideal voltage source through this inductor. If we run a simulation, we see that the 5-volt voltage and 5-amp current waveforms are completely ideal. There is no overlap of voltage and current due to the instantaneous switching. Thus, we cannot multiply the voltage and current to obtain the switching losses. Additionally, there is no voltage drop when the device is conducting, so the conduction losses are also zero. We are now going to introduce the thermal domain in PLECS. If we double-click on the IGBT in the circuit, you will notice a thermal description parameter. In order to specify a new thermal description, choose this option from the drop-down menu. This opens up a thermal editor using several tabbed panes. The thermal editor facilitates the editing of switching losses, conduction losses, and the thermal equivalent circuit of a component. The text entries manufacturer, part number, and comment are for documentation purposes only. The type selector serves as a filter for the thermal description menu entry. It must be set to the semiconductor type it is intended to be used with. Switching losses are defined as 3D lookup tables in the first two tabs for the turn on and turn off losses. The energy for each switching event depends on the blocking voltage, the device current, and the device temperature. New data points for temperature, voltage, and current are added and removed with the Edit menu or the Context menu in the table by right-clicking. Multiple values can be added if separated by semicolons or spaces. Users can specify the unit of the losses by using the Energy Scale drop-down box at the top right. Let's now add a few data points to create a loss surface for 25 degrees. You can also copy and paste thermal data within the tables of the thermal editor and to or from other programs such as Microsoft Excel. This can be done using the Context menu or by pressing the keyboard shortcuts for copy and paste for your specific operating system. Let's copy the loss information for the turn-on losses to the turn-off table as an example. We first need to set the voltage and current values and choose the appropriate unit for the losses. Let's now move on to the next tab, where conduction losses are defined by means of a 2D lookup table. The conduction losses are computed by PLECS in a straightforward manner, as the product of the device current and the device voltage. The conduction loss table allows you to specify the on-state voltage used for the loss calculation as a function of the device current and the device temperature. Adding and removing entries here is done in the same fashion as with the switching losses. The thermal interface from the junction to the case can be represented in a lumped fashion using the thermal resistors and capacitors. They can be defined in the Thermal Impedance tab. A more detailed description for this tab is provided in a second video on thermal modeling. If we hit the OK button, we can then save the loss description as an XML file. For simplicity, we will save the file to the desktop. We must now add the desktop to the thermal description search path. The search path for the thermal libraries is specified in the Thermal tab of the PLECS Preference window. We can select the thermal description for the simplified IGBT from the block parameter window. Returning to our schematic, we will now incorporate components from the thermal library to model the thermal circuit. The key block for the thermal domain library is an idealized heatsink, which is essentially a surface of equal temperature. The heatsink absorbs the thermal losses dissipated by the components within its boundaries. At the same time, it propagates its temperature to the components that it encloses. As we want to be able to monitor the losses and temperature of our IGBT, we will place a heatsink on it. Each heatsink has an intrinsic thermal capacitance. All thermal losses absorbed by the heatsink flows into this capacitance and therefore raises the heatsink temperature. Heat exchange with the environment occurs via the external connectors. Heat conduction from one heatsink to another or to an ambient temperature can be modeled with lumped resistances and capacitances that are connected to the heatsinks. This approach allows you to control the level of detail of the thermal model. For this example, we will model the environment using a fixed temperature source. We will choose a thermal resistance of 1 Kelvin per watt. We will also set the thermal capacitance of the heatsink to 5 millijoules per Kelvin and its initial temperature to match that of the ambient environment at 25 degrees. Now that we have defined our thermal circuit, we will monitor the temperature of the device and the power flowing from the heatsink to the ambient. We will grab a PLECS probe component from the system component library. The PLECS probe enables you to monitor various signals associated with the component. Most PLECS components provide one or more probe signals that describe their current state as well as their input or output signals. For instance, the probe signals of an IGBT are the device's voltage, current, gate signal, and conduction state, as well as its junction temperature and losses. If we double-click on the probe icon, it will open an editor window, and from here we can drag the IGBT into the box in the center. The list on the left shows the components that you have selected for probing. The components are identified by their type, name, and path within the circuit. The list on the right shows the available probe signals for the selected component. Use the checkbox next to the signal names in order to enable or disable individual signals. We will now add the heatsink to the component list. Another way to do this is to drag the device of interest onto the probe block in the schematic directly. This will append the component at the bottom of the list. We can reorder and delete the components in the list by using the up, down, and remove buttons. We will measure the heatsink temperature. We will use a signal demultiplexer component to separate the IGBT conduction state and heatsink temperature signals and plot them in two separate plot windows. Let's also connect a heat flow meter to the thermal circuit and send this measurement to the scope. If we run a new simulation and look at the scope in the top right, we see that during the conduction interval and the switching instances, there is an increase in temperature and dissipated power. While the device is off, it does not experience any losses. During this interval, the device is cooling down. This concludes our introduction to thermal modeling in PLECS. So far, we have shown the basic use of the thermal loss descriptions as well as some of the discrete components of the thermal library. A second video follows with demonstrations of a thermal simulation with more complete analysis.